So in this video, we're going to be looking at carboxylic acids, their shape, structure, and their reactivity as well. Now, starting off, right, carboxylic acids, they have a characteristic carboxyl, a Cu group, right? And we know that we can find that at the end of the carbon chain where we've got carbon double bonded to an oxygen, and that same carbon atom is also going to be bonded to OH itself as well. We end up with a variable R group where we can end up with things like methanoic acid, ethanoic acid, and propanoic acid, and so on. And we know that carboxylic acids, right, if we were to look at them in structural formula, yes, we do end up with a Cu group, right, in structural formula, but we could also end up with the reverse as well when dealing with more complicated carboxylic acids itself as well. Now, carboxylic acids are going to be soluble in water, and the reason why is because they can form hydrogen bonds with molecules of water. And we can actually draw a hydrogen bonding diagram for a carboxylic acid. And remember, carboxylic acids, they contain an OH bond where oxygen is going to be more electronegative compared to hydrogen and carbon, and so we know it's got a greater ability to attract electrons in a covalent bond. So that's going to be delta negative. The hydrogen here is delta positive, the carbon here is going to be delta positive, and then the oxygen here is going to be delta negative as well. We know we've got a lone pair of electrons which we can start our hydrogen bond from, or we can actually start it from the hydrogen in this case, which is what I'm going to do, where I start to draw my hydrogen bond with some dashed lines, and then I draw that going towards a lone pair on an oxygen atom itself. And then remember, oxygen has two lone pairs, but the hydrogen bond comes from one itself. Again, we're going to have a molecule of water, so we've got an OH bond there and another one there. It's a non-linear molecule, so I've just turned it around a bit to draw a nicer diagram. I've got delta plus on my hydrogens and then delta negative on my oxygen itself. I need a label. I'll put label on there because a good diagram always has a label, and that's going to be our hydrogen bond itself. Now, normally you do actually get 2 marks for this, but just remember that you can also draw a hydrogen bonding diagram to show why ethanoic acid or any carboxylic acid really has a higher boiling point compared to something like ethane itself. Now, carboxylic acids themselves, they have a relatively high boiling point, and that's because of the hydrogen bonding between the molecules, which requires a relatively higher amount of energy to overcome compared to things like induced dipole-dipole interactions and permanent dipole-dipole interactions. Now, when we look at hydrogen bonding, right, we know that this can happen between 2 molecules of, let's say, ethanoic acid, and so our diagram will just change where I end up flipping a molecule of ethanoic acid, and I draw my hydrogen bond going from my H to my oxygen's lone pair itself. Now, coming back to solubility, we know the longer the non-polar alkyl chain is actually going to be in our carboxylic acid, the less soluble it will be in water. And you can see out of the two of ethanoic acid compared to nonanoic acid, right, because nonanoic acid has a longer non-polar alkyl chain, right, it is going to be less soluble in water itself. Remember, the alkyl chain over here is not soluble, right, that doesn't form hydrogen bonds between the actual carboxylic acid and the molecules of water. It's actually the carboxyl group that does it itself as well. Now, that's very important because if you were to look at dioic acids or dicarboxylic acids or whatever you want to call them, they actually have 2 carboxylic acid groups, one at either side of the chain, and they're going to be more soluble because they form more hydrogen bonds with molecules of water. So in this case, we've got ethane dioic acid that's more soluble in water compared to ethanoic acid because it forms more hydrogen bonds to water itself. Now, looking at our carbon-carbon-oxygen bond angle, we've got a bond angle of 120 degrees, and although you might think that we've got 4 bonded pairs and 0 lone pairs, which we actually do around the carbon atom, they're split into 3 regions of electron density, or 3 bonding regions itself. And what that means is that they repel each other as much as they possibly can, so all electron pairs repel to get as far away as possible, and so we end up treating that double bond as a region of electron density. So all of these regions of electron densities are going to repel as far as possible, and we approximately get a bond angle of 120 degrees itself. Our shape is trigonoplanar. Now, looking at our COH bond angle, we've got a bond angle of 104.5 degrees, and we know that we've got a non-linear shape here. Now, the reason why is because we've got 2 bonded pairs and 2 lone pairs in this case. The lone pairs are going to repel more than the bonded pairs, and so rather than having the bond angle of 109.5 degrees, we actually end up with a more squished shape itself. Again, all of our electron pairs, they're going to repel, right, but the lone pairs repel more strongly than bonded pairs, and so that gives rise to our bond angle of 104.5 degrees and a shape that's going to be non-linear itself, just like water. Now moving on, if we were to look at reactivity, carboxylic acids, they react like any other acids to be honest, but carboxylic acids are generally weak and they partially dissociate. Now if you were to look at the reactions, they react like pretty much any other acid, where let's say if they were to react with a metal, you'd end up with a redox reaction. The H plus is going to be reduced to a H, hydrogen itself, hydrogen gas, and we actually end up with fission taking place, and metals, they're going to dissolve because we end up forming the salt itself. Remember what a salt is? It's when the H plus of an acid is replaced with a metal or an ammonium ion itself. Now in the next case, we've got an acid reacting with a metal oxide. That metal oxide dissolves, and what we end up forming is salt and water. Acids with metal hydroxides, you've got to look at the state symbols over here. If we're dealing with a metal hydroxide, if it's a solid, it will dissolve. If it's going to be aqueous, then you see no visible change itself. And the same is going to be with a metal carbonate, where your solid will dissolve if it is going to be a solid. If it's going to be aqueous, then you end up with no visible change on the solid part, but then you always end up with carbon dioxide gas being released, and so you would be able to see fission itself. Now moving on, I've got some examples for you to try in structural formula. Feel free to pause the video and have a go at the following. So yeah, looking at propanoic acid, then we've got a formula of CH3, CH2, and then it's going to be COOH itself, and that's going to react with sodium in a redox reaction, where we know that sodium is going to form a sodium plus ion, and then we also know that we're going to form a propanoate ion. The salt we form is going to be sodium propanoate, which would be CH3, CH2, COOH itself, but remember that H has been swapped out for a sodium, so in that case we end up with an ionic bond between the oxygen and sodium itself. Now in this case, I also form hydrogen gas, so we expect to see fission, and to make it balance, I'm going to have half a lot of hydrogen itself, and that's our first one done. Looking at the next one, we've got ethanoic acid reacting with magnesium carbonate. So I've got CH3COOH reacts with magnesium carbonate, which is Mg. Because magnesium is 2+, we only need one carbonate ion, and we end up forming over here, right, a carboxylic acid ion, which is going to be a carboxylate ion, which in this case is an ethanoate ion. But remember, to make this balanced, because the charge of ethanoate is going to be 1-, we end up with 2 lots to balance the charge of magnesium 2+ itself. You can use the drop and swap method, or you can just get straight stuck into it, but just remember to take into account the charge of the metal itself. Now I also form water, and then I also form a carbon dioxide molecule as well, and just remember you need to balance this, so you need 2 lots of ethanoic acid, and there's the next one done. Looking at ethane dioic acid and lithium hydroxide. Now ethane dioic acid is actually going to be a dicarboxylic acid. We've got 2 carboxylic acid groups on there. Just remember the structure. You end up with something that looks like this, where you've got a carboxylic acid functional group here, and then over here as well, join in the OHs, and it's going to be a diprotic or dibasic acid, whichever one you want to call it, where we swap out this hydrogen and that hydrogen for our metal ions itself. So in this case, I end up with, yes, COOH, but then on the other side, I also end up with COOH this way as well. And there's a formula of ethane dioic acid. Now that's going to react with, in this case, it's going to be lithium hydroxide, and we end up forming our salt, where we end up with our CCOO, and then it's going to be minus minus on either side, but we swap it, that hydrogen with lithiums, and then we also form water. Now to balance this, I'm going to need 2 lots of lithium hydroxide, and I form 2 lots of water. And let's say if lithium hydroxide were a solid, it would dissolve, but then if it was aqueous, then we would end up with no visible change. The next one, we've got benzoic acid, and just remember, benzoic acid is going to look like this. We've got benzene ring, a carbon atom, and then I've got a carboxylic acid attached to it as well, which looks like this, and that H over here is going to be what's going to be replaced itself. So in this case, I've got C6H5. Remember, benzene is C6H6. If we swap one of the hydrogens out, we end up with a carboxylic acid, and then that C6H5 is going to have a CO group on it as well. We end up with that reacting with magnesium oxide, which again is a metal oxide, and so we form a salt and water. Our salt in this case is going to be magnesium benzoate, because we form a benzoate ion, and so I'm going to have 2 lots of benzoate ions actually, because magnesium's 2+, we need to get that to balance, and so that's going to be C6H5 and then COO. in brackets, and then 2 lots of it with magnesium, and then we also form water as well, right? That water, 2 lots of hydrogen has come from 2 lots of benzoic acids, so I need 2 lots of that, and then 1 oxygen has come from the magnesium oxide itself, and there's that one done. Now moving on, right, that summarizes our reactions of our carboxylic acids, but we also need to compare them with phenols and alcohols as well. Now carboxylic acids, they react with metals, metal hydroxides and metal carbonates, right, whereas phenol, that is too weak of an acid to react with metal carbonates. Now alcohols, they're not going to be acidic like carboxylic acids and phenol, but they do react with metals, and they do actually fizz when they react with metals as well. Now let's say if we were to look at our functional groups, we know that alcohol they're neutral. Phenol is going to be a very weak acid, and then carboxylic acids, they're going to be slightly stronger compared to phenol, but they're going to be weak acids still. With metals, all 3 of them will fizz, but then with metal hydroxides, right, only your phenol and carboxylic acids will react with them. If you were to look at their reactions with metal carbonates, carboxylic acids is going to be the only thing that reacts with your metal carbonates itself as well. So moving on then, I've got a task for you to do. Feel free to pause the video and have a go. So yeah, which of sodium hydroxide or sodium carbonate will the following react with? Well, in the case of ethanol, remember it's not acidic. The only thing it does react with is sodium, and what you actually end up forming is, in this case, you've got sodium ethoxide, right? So you've got ethoxide, which is an ion that looks like this, 2 carbon atoms, and then an oxygen, and then the H plus is going to be replaced with the sodium metal itself, which looks like this. With phenol, right, phenoxide is the ion that you actually form when you react with sodium and sodium hydroxide. Not strong enough of an acid to react with sodium carbonate, and so you end up with your benzene ring over here, and then you've got your phenol, which becomes phenoxide, and that's going to react with sodium and sodium hydroxide. In both cases you form a salt that looks like this. What about ethanoic acid? Well, ethanoic acid can react with all 3 of them. Sodium, it's going to react with sodium hydroxide as well as sodium carbonate as well. And in all 3 cases, you end up forming, yes, ethanoic acid, which is going to form an ethanoate ion, and then that's going to be bonded, ionic bond between the sodium ion as well, so you form sodium ethanoate. The equation for the reaction between methanol and potassium, well, methanol is going to be CH3OH, that's going to react with potassium, and what you actually end up forming is potassium methoxide, and so that's going to be CH3, replace the H with the K, and you form potassium methoxide, and then you also form hydrogen gas. Let's make that balance. I can double everything up, and I end up with 2 lots of hydrogen itself. Could have halved it as well, but in this case, right, we're going to go with whole numbers.